we're going to look at how we can use and apply the chain rule to find the derivatives of implicit functions, or excuse me, implicit equations, a technique known as implicit differentiation. So first off, implicit equations may have been encountered in prior classes, but maybe not, so it's worth it going over. So an implicit equation is an equation where y is not an explicit variable, i.e. a variable by itself, y equals f of x, but rather is hidden in the equation. So some examples is the equation of a circle of radius r, x squared plus y squared equals r squared. The reason being is that y is hidden here. Keep forgetting my pointer. That y is hidden here, and any attempt to solve for y cannot be done, because if we do this, we're going to take the square root of y, which gives two different solutions, plus square root of r squared minus x squared, and y equals r negative square root of r squared minus x squared. Another example would be x squared plus 2y squared divided by y equals 6. So the first thing that we're going to look at is how to locate points of an implicit equation provided a coordinate. So for example, let's locate all points in the curve x squared plus 2y squared divided by y equals 6, where x equals 4. So the main idea here is not too bad. It's just we're going to plug the known x value or y value into our equation to find the corresponding y or x value. Determine if such a point is even possible, which is something that pops up quite frequently on the free response section, as we'll see in class tomorrow. So x squared or x plus 2y squared equals 6 divided by y. We plug in x equals 4, so we get 4 plus 2y squared divided by y equals 6. Solving the resulting equation gives us 4 plus 2y squared equals 6y. We move this over to get 2y squared minus 6y plus 4, which we can factor into 2y minus 2, y minus 2 equals 0. So we see that when x equals 4, there is the corresponding y coordinates of y equals 1 and 2. So x equals 4, y equals 1, and x equals 4, y equals 2 are both points on our implicit equation. So now, a familiar question that's asked, and this appears quite frequently on the exam, is it possible that there's a coordinate or point on the curve with an x coordinate or y coordinate, blah, blah, blah. So an example here is it possible that there's a point on the curve x minus 2y of 4 equals 30 with an x coordinate x equals negative 2. The idea behind this is you're still going to plug in x equals negative 2. So you're still going to do the same thing we've done here, but now what you're going to see is that the answer you're going to get, is it possible or not, depends on the answer for y you get. So you're still going to solve for y, but your answer is going to depend on what y is. So in this case right here, we're going to get x minus 2y to 4 equals 30. We plug in x equals negative 2 to get negative 2 minus 2y to 4 equals 30. And thus solving, we're going to get negative 2y to the 4th equals 32, or y to the 4th equals negative 16. If we find the solution to this, we're going to get y equals the quintic root of negative 16, that's a fancy word, quintic root, which is going to equal plus or minus 2i. So the answer to this equation, again, lies in finding y, and we see that, in fact, it is not possible that there's an x-coordinate on the curve of x equals negative 2, because we see that when we solve for the corresponding y-coordinate, we get an imaginary number, which is not possible because all numbers we work with in calculus are real numbers. So thus, that's the logic that you want to apply to these type of questions when it's asked, is it possible? So now let's look at how to differentiate an implicit equation. So what we're going to do is we're going to start off with an example from the chain rule where we have h of x equals f of x to the 4th power. If we apply the chain rule to take the derivative of this, as we've done in class, we'll get 4 times f of x cubed times the derivative of f of x. Again, f is our inner function, so the derivative of, so f is our inner function, our outer function is something to the 4th power, so our derivative is going to be 4 times f cubed times the derivative of f with respect to x. So now what we're going to do is we're going to substitute h of x equals x and f of x equals 1 into the above result in order to get h prime of x is going to be 1, and then the right-hand side is just going to be 4y cubed times y prime. We'll see y in a second, okay? So comparing our results, we have h of x, we have f of x to the 4th. When we plug in x, we're going to get y to, when we plug in x for h of x, we're going to get the derivative is just 1. And then when we plug in f of x to the 4th power, we plug in y, we're going to get the derivative as 4y cubed times y. just by applying the chain rule. So what this means is that if we want to differentiate an implicit equation, we're going to proceed as we normally do with derivatives, except that whenever we come across an expression containing y, like we did right here, we're going to apply the chain rule to the result. So as a result, if we had y to the fourth right here, so now we're working back, we have h of x equals f of x to the fourth. We're just summarizing results. So we're replacing h of x with x and f of x with y. Okay, we see that when we take the derivative of both sides, we're going to get the derivative of x is 1, and then the derivative of y to the fourth, we're going to apply the chain rule to. Y is an inner function here. It's an unknown inner function. So we're going to apply a chain rule where we get 4y cubed multiplied by the derivative of y. And thus the last step that we're going to do is we're going to solve for y prime. So we divide both sides by 4y cubed, which gives us that the derivative of this implicit equation is 1 over 4y cubed, our end result. Some more examples here, just to hammer a point home, is if we have natural logarithm of y equals x, okay, taking the derivative of both sides means that we're going to have the derivative of 1 over y, since the derivative of the natural logarithm is 1 over whatever our variable is, times y prime, the derivative of y. And then the right-hand side is going to be equal to 1, the derivative of x. And then dividing both sides, or excuse me, multiplying both sides by y to isolate y prime, we get y prime equals y. If we look at the second case, if we have y cubed equals e to the x, okay, taking derivatives of both sides, we see that first off, the easy side, the right side, e to the x, the derivative of that's just going to be e to the x. Now the derivative of y cubed, we apply the chain rule with the power rule to that. We're going to get 3y squared times y prime. And thus solving for y prime, we're going to get y prime equals e to the x divided by 3y squared. And then lastly, one more point just to hammer the point home, is that if we have tangent of y minus 4x equals x squared, taking derivatives of both sides, the derivative of tangent is going to be secant, secant squared, so we're going to have secant squared of y times the derivative of y, and then we're going to take the derivative of minus 4x, which is just minus 4, and then the derivative of x squared, which is just 2x. So solving for y prime by moving 4 to the other side, ooh, I messed up. This should be a plus 4, not a minus 4. So we're going to get 2x plus 4 right here, and then we're going to divide both sides by secant squared of y in order to get y prime by itself. So we get y prime equals 2x plus 4, ignoring my stupid typo, divided by secant squared of y. And that gives us our derivative of our implicit equation. So now let's look at a more complex case where we have x cubed plus 9 plus y cubed minus 9xy equals 0. And we want to determine dy over dx for the curve. So what we're going to do here is we're going to work our way from the outside in, applying the rules as appropriate, just like we did in 2.5. And then what's going to happen is we're going to move all terms that contain dy over dx to one side, and then move the remaining terms over to the other side. So let's see what this looks like in practice. So we take the derivative of both sides. We're going to have x cubed, the derivative of that is going to be 3x squared. Y cubed, to the derivative of that will be 3y squared times y. And then we can factor out the 9 to take the derivative of just xy. Notice that x times y, we're going to have to apply the product rule to. So we take the derivative of x times y plus x times the derivative of y. In this case, since we just have y by itself, it's not y to the first or secant of y or anything like that. We just write y prime since that's the derivative of y. Okay? So in the next stage, we see that the derivative of x prime is just 1. So as a result, we have 3x squared plus 3y squared times y prime minus 9 times y plus x times y prime. So now what we're going to do is we're going to simplify and group all terms that contain y prime together to one side and move everything that contains that doesn't contain y prime to the other side. So we have 3x squared times plus 3y squared times y prime. Distributing this negative 9 right here, we're going to have negative 9y minus 9x times y prime. So now what we can do here is we notice the 3y squared and the negative 9x both contain y prime. So we're going to have 3y squared minus 9x times y prime. And then we're going to move the 9y to the other side, so we add 9y to both sides, and we subtract 3x squared from both sides since these do not contain y prime. So now, lastly, what we're going to do is we divide both sides by 3x squared minus 9x in order to get our expression by itself, or our derivative by itself. So we see that our derivative is 9y minus 3x squared divided by 3y squared minus 9x. And this is the case for these are the cases for implicit differentiation. This one is a little bit more drawn out than the rest, so we'll spend more time looking at these types of problems in class, especially as pertains to the free response section of the AP Calculus exam.